Hi guys, so we're going to work on Regents Prep 7, Physical Behavior of Matter. So hopefully you have your reference table right by you and your calculator. And we're going to start with a multiple choice. So multiple choice, the temperature required to change 1 gram of solid at its normal melting point to a liquid at the same temperature. So I'm going solid to liquid. So they want to know what that's called. So heat of, well, that is going to be heat of fusion. You want to remember fusion is always going to be associated with the words melt or freeze. And here I'm melting if I'm going from solid to liquid. You're not going to want these two. If you think of vaporization, though, you can think of, you're going to think steam, vapor, boil, condense. So 2, the graph below represents the uniform heating of a substance starting below its melting point as a solid. So I can already go ahead and label that this must be solid, this will be liquid, this will be gas. So it said which line segment represents an increase in the average kinetic energy. You want to remember that average kinetic energy always means the temperature. So I want an increase in my temperature. So I'm noticing that my temperature is over here. So my temperature is changing in A, B, C, D, and E, F. So let's see if we can find a choice that has that. A, B, B, C, I don't like B, C. A, B, C, D, yep, I like this one. And the other ones I don't like, again, I don't like B, C. I don't like D, E. I don't like D, E, but I do like E, F. Yep, I like B. Number 3. Which grouping of the 3 phases of bromine is listed in order from left to right for increasing distance between the molecules? So increasing distance. So I want to think, well, when I draw a solid, it would look like that. When I draw a liquid, it would be a little more spread apart, not too much more. And then a gas would be very spread apart. So solid, liquid, gas would be increasing distance. So I like choice D. 4. Which phase change is accompanied by a release of heat? So I want to think release of heat. That must mean I'm cooling. So if I'm going through a cooling phase change, I want to think, okay, solid to liquid, I would be melting. And so I would be heating. So it's not A. It's also not going to be C or D because solid to gas, well, that's sublimation, but that's heat. And liquid to gas, well, that's when I boil, and that's definitely when I heat. So C and D, so it's got to be B. But if we explain that, liquid to solid, that's where you freeze. And if you freeze, you are cooling. 5, when a substance melts, it undergoes a process known as, so I like that keyword melt. Melting is fusion. Melting is fusion. 6, which Celsius temperature is equivalent to 323 K? I remember that on my reference table, I have the temperature calculation equation. So K equals degrees C plus 273. So I'm going to just write that. K equals degrees C plus 273. Well, they're telling me they want to know which Celsius temperature is equal to 323 K. So if I do 323 equals X plus 273, essentially I'm just subtracting 273. So subtract 273, and you're going to get 50. 50 degrees Celsius. I can always double check because if I do 50 plus 273, I'm going to get that 323 again. 7, which graph represents a change of phase from gas to solid? Well, if I go from gas to solid, I'm cooling. So I want to look at a cooling diagram. It's not going to be pressure and time. I don't like pressure. I'm not talking about that, but I am talking about temperature. So if I go from a gas to solid and I'm cooling, gas, liquid, solid, I like choice 1. Cooling heating curve. Okay, number 8. When steam condenses to water, so steam is condensing to water. Focus on that condensation. Condensation is when I go from a gas to a liquid. So it wants to know about the surrounding temperature. Well, if I go from a gas to a liquid, what I'm actually doing is I'm cooling. So if I'm cooling, that means I have to release some heat. So if I release some heat, that surrounding temperature, I'm going to feel that release of heat. So the surrounding temperature actually increases because the actual water is cooling. This one's a little bit tricky. 9. Which of the following is a unit of heat? Well, heat, I can always look actually on my reference table over here. I could see if any of these will help me. In table D, it has my selected units. So I could kind of search and see if I'm doing heat, and I see heat right here, the joule. So I can come over here and pick joule. So table D would actually help me if you forget. But a lot of people want to think heat, you want to think of Q, and Q is your heat, and that's your joules. 10. As temperature of a substance rises, the average kinetic energy of the particles making up the substance. So temperature is rising. They want to know up the average kinetic energy. Well, the average kinetic energy is your temperature. So if you increase your temp, you're going to increase your kinetic energy because they're the same thing. So B. By definition. 11. Which energy transfer occurs when ice cubes are placed in water that has a temperature of 45? So I'm putting the ice into the water. So ice, I want to think of, well, that'd be at about 0 degrees Celsius. And it's going to water with 45. Heat's always going to transfer from hot to cold. So I want to think, well, hot would be the 45, so that's my water. Colder would be my ice. So it goes from the water to the ice. So I want to think, wait, chemical energy or thermal energy? Well, thermal energy is what I actually want. I don't like this chemical energy. So A and C are out. So it goes from the ice to the water to the ice. We just said hot to cold. So D, from the water to the ice. And again, if I want to further explain, water is at 45 degrees Celsius. The ice is at 0 degrees Celsius. 12. Liquid's freezing point is negative 38, and its boiling point is 357. How many kelvins is there between the boiling point and the freezing point? Well, actually, you don't have to think that hard, because if I convert both of those to Kelvin, it'll be the exact same thing if I just subtract them there. So boiling was at 357, and I'm going to subtract negative 38. And if I do that, I'm going to get 395. You also could take both of these and convert them to kelvins if you wanted to. So you would just subtract 273, but you actually don't need to because it's a change in temperature. So, because they're asking for it between the boiling point and the freezing point. So it's a change. Remember, triangle means change. 13. Which set of properties does a substance such as CO2 have? Well, it told me that it's gas, and that's what I want to focus on. It's a gas. So gases, do they have a definite shape or a definite volume? Neither. So not definite shape, not a definite volume, not a definite shape. No shape, but definite volume. Nope, I don't like definite volume. No shape, no volume. I like that. And if I want to prove it, I can draw a picture. If I were to take a box and have a gas, it would spread itself out. 14. A liquid is poured from a volumetric flask into a beaker. Which of the following is true? So I have a liquid, and they're taking it from a flask into a beaker. So does it retain its volume or its shape or both? Well, it's not going to retain its shape because a flask is a different shape than a beaker. So, but it will retain its volume. So volume, yes. Shape, no. So A is out. Retains volume, yes, but shape changes. Yes, shape changes. I like B. So liquids have a definite volume, but not a definite shape. 15. A solid is heated at a constant rate. Its temperature increases from 10 to 25 degrees Celsius, remains at 25 degrees Celsius for 5 minutes, and then it increases beyond 45 degrees Celsius. Based on information, what conclusion can be drawn? So we know we started as a solid, so a solid was heating. And if it was heating, then I was probably going from a solid to a liquid. And if I do that, solid to liquid, I'm melting. And where it said this is the key part, it remains there for 5 minutes. Remember, if I'm looking at one of those heating curves, I heat, then I stay steady, then I heat, then I stay steady, then I heat. So they're talking about it right here, where there would be no temperature change. That's right there. So they're talking about the melting point, and the melting point would be at, so not boiling, melting point would be at 25. 16. Which statement best describes the molecules of H2O in the solid phase? So they move either slowly or rapidly. Well, they're definitely not rapid. Maybe slowly. I don't really like the straight lines. They just kind of vibrate. So I don't like that. They're arranged in a regular geometric pattern. Yes, I actually really like that, because if I were to draw a solid, I would draw it just like that, in nice lines and rows. So they're not random. So I like C. Okay. So they give me 17 and 18 look at this. It shows a compound. So the compound's being cooled at a constant rate. This is important. It starts as a liquid at 75 and ends at 15. So this would actually be the liquid phase. That must mean this is solid. That might be important to us. So 17, state what is happening to the average kinetic energy of the sample between minutes 2 and 6. Well, here's minute 2. Here's minute 6. So they're asking me to look right here. What's happening to the average kinetic energy? Well, it's not changing because no temp change. So no temp change there, which means the average kinetic energy remains the same. Or you could say constant. Either one of those. 18. What is the freezing point of a compound in degrees Celsius? So I want to know, where does it freeze? Well, this is freezing right here. The freezing point is the very first time where you're going to see solid. So remember that if this is liquid, then here I would have liquid and solid. So right here would be my freezing point. That's the first point where I would see any solid there. So that occurs at a temperature of 50. So 50 degrees Celsius. Okay, so they're giving me a data table right here. And it says for 19, mark an appropriate scale on the axis labeled volume. So I have to scale it, plot the data, and connect the points. So let's kind of look what I'm looking at here. Let me turn the page. So they already put my pressure on. I want to do the volume. I notice that the volume is going to go, here I can put it on a different one. The volume is changing. It goes 1200, 600, 300, 150, and 100. So if I was going to scale that, I think based on what I have there, I should go maybe by, I want to spread it out. Maybe let's go by 200s. So this would be 200. That would be 400. This would be 600. Here, I'll go down like this. 800. 1,000. 1,200. That would be 1,400. That would give us plenty of room. So I scaled it. Now I'm going to put it on. So volume was 1,200. Pressure was 0.5. So So 1200.5. Then I had pressure was 1. Volume was at 600. So 600, it's 1. At 300, which we right in here, pressure is 2.0. At 150, which would be right about here, because that'd be 100, be right here. So 150, it's at 4. And at 100, which would be right in the middle, it's 6. And it said to circle and connect the points. So circle, 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 circle. And I'm going to connect my points. Boom. So 20 says, based on your graph, what is the pressure of the gas when the volume of the gas is 200? So you're just going to go up when the volume is 200. Let's read where your graph is. 200. Mine looks to be at about 3.0 ATM. Now this will depend on your graph. So you got to look at your graph. But what you do, go up to the 200 and see where it hits the line. 21. A light bulb contains argon gas at a temperature of 295 K and a pressure of 75 kilopascals. Light bulb is switched on, and after 30 minutes, the temperature of 418 K. The volume of the bulb remains constant. So volume's constant. What is the pressure at 418? So they want pressure. So I have a temperature, that's probably T1. I have the kilopascal, that's a pressure, that's P1. My T2, because there's a second temperature, this would be P2. I'm actually looking to do a combined gas law. So combined gas law, I actually wrote on this reference table. So here's my combined gas law. But they said volume's constant. So remember, if volume's constant, you just take it right out. So actually, if you look at this one, I crossed off volume. So P1 over T1 equals P2 over T2. I'll write that. P1 over T1 equals P2 over T2. So I can put numbers in for that. P1 was 75. T1 was 295. Your P2 was X. You know your second temperature was 418. You're going to solve for that X. You're going to get X equals 106.3. I need a unit, and it's kPa. kPa, because that was what my pressure was in. So here, the next one, I'm going to use this for 22 to 25. So I'm going to read this. It says, a cylinder contains 22 grams of CO2 and cylinder B contains N2. The volumes, pressures, and temperatures of the two samples indicated under each cylinder. The cylinders are fitted with movable pistons. And I see we have a volume, a pressure, a temperature, and a volume, pressure, and temperature for cylinder B. And actually, I'm going to notice that these are the exact same. So I'm going to just note that these are the same. So, okay, let's go to the question side. 22. Explain why the number of molecules N2 in cylinder B is the same as the number of molecules CO2. So whenever they ask this question, why do you have the same number of molecules, I want you to think this is Avogadro's law. And Avogadro said that if your pressure, volume, and temperature are the same, so pressure, volume, temperature are the same, then they will have the same number of molecules. So you want to say that all three of those variables, pressure, volume, and temperature, were all held the same for both cylinders. And again, I can prove it right here. Volume, pressure, temperature, they're the same. Number 23, what's the total number of moles CO2 in cylinder A? Well, I want to be careful because if I go back, they told me that I had 22 grams of CO2. So if I'm going to do moles, I actually want to use my mole equation. My mole equation is my given mass over your gram formula mass. Remember, I can find that right on table T for my mole calculations. So I know that my mass they gave me instead of 22.0 grams, and my gram formula mass is CO2. Well, that's 12 times 1 plus 16 times 2. That's 44. So 22 over 44 grams per mole. That means your moles is 0.5. So be careful. That's how I wanted to do that one, using my mole equation. 24. The piston in cylinder B is pushed until the volume is 6.0 liters. If the temperature remains constant, what is the new pressure? So new pressure, I want to think that's probably a P2. And I push cylinder B till it's that, so that's probably a V2. So let's take again a look at our cylinder B. Well, I know a volume is 12.3, and a pressure is 1.0, and my temperature is 300. So I'm just going to write that down. I know my volume 1 is 12.3 liters, and I know my pressure 1 was 1.0 atmospheres. I also knew my temperature, but they told me it remained constant. So again, I'm doing combined gas law, only now I don't have a temperature. So if I do that, it actually changes over to here, because remember, I just cover up my temperature. So P1 times V1 is P2 times V2, P1 V1, P2 V2. So I'm going to say, okay, P1 was 1, V1 was 12.3, P2 is X, new volume is 6.0. I'm going to solve for that X, and I'm going to get X equals 2.0 ATM. If you wanted, you could have left in that temperature, and you could have used the whole combined gas law, but you didn't have to for that one. 25. Temperature of CO2 is increased to 450 K, and the volume of the cylinder remains constant. What is the new pressure of CO2 in cylinder A? So again, I'm going to go back. I'm going to look at my cylinders. In cylinder A, I knew I had a volume of 12.3. I knew I had a pressure of 1.0, and I knew I had a temperature of 300. So my P1 was 1.0 ATM, V1 was 12.3 liters, and T1 was 300. The volume staying the same, so I don't care, but my T2 is going up to 450, and P2 is X. I don't know what that is. So I'm going to actually get rid of that volume. I don't care. So again, I'm setting up here. I'm going to use this equation where I take out the volumes because it's constant. So P1 over T1 equals P2 over T2. Let's put our numbers in. So I have 1.0 over 300 equals X over 450. I solve for X. X equals 1.5 atmospheres. 1.5 atmospheres. Sorry, keep going off the screen there. Okay, now I have some more assorted questions. So I don't necessarily go with anything else. See if we can figure these out. So it says, how many joules of energy are needed to convert 50 grams of water at 50 degrees Celsius to 65? They're asking for joules. I want to think joules is Q. That's heat. I'm going to want to go to these heat equations and see, am I going to want to use MCAT? Am I going to use Q equals MHF? Or Q equals MHV? So I'm going to say, well, I have a change in temperature right here. I know it's water. 50 grams is the mass. And I'm looking for Q. It looks like I'm going to use MCAT. Q equals MC delta T. So I say, okay, M is 50. My C, for specific heat for water, go to the very first part of your reference table. This gives you physical constants. C is your specific heat capacity. So it's 4.18. And that change in temperature from 50 to 65. So that change in temperature is 15 degrees Celsius. So I'm going to multiply by 15. So I'm going to get Q equals 3,135 joules. 27. How many joules, Q, are needed to completely boil, think HV, 40 grams of water at 100 degrees Celsius? So boil leaves me HV. I'm going to go, again, back to my back page of my reference table. This time I'm going to grab Q equals MHV. So I say, okay, well, my M is 40.0. My V, again, go to table B. Heat of vaporization is HV, 2,260. 40 times 2260, that's going to give me 90,400 joules. 90,400 joules. 28. A substance has a specific heat capacity of 2.0. How many joules are needed to raise the temperature of 30 grams of the substance by 15? So they didn't tell me my initial and final temperatures, but it's raising the temperature by 15. So this means the change in temperature is 15 degrees Celsius. That's your mass. And they're giving me a specific heat. That's C. So they give me enough to use Q equals MC delta T. It's just this time I'm not going to use 4.18 because it's not water. They didn't tell me water at all, so I'm going to use what they gave me. So mass was 30, specific heat was 2, and change in temperature was 15. So that's going to give me Q equals 900 joules. Last one. What volume will 250 milliliters of gas at STP occupy if the pressure changes to 2.0 atmospheres and the temperature changes to 30 degrees Celsius? Okay, so I'm going to think, what do I have? This is 100% going to be my combined gas law. P1, V1, T1 over T1 equals P2, V2 over T2. So I'm going to think, okay, what do I have? So what volume will 250 milliliters of gas at STP? All right, this gives me a lot of things. 250 milliliters, that's my V1. STP, I can go in my reference table, and I got my standard pressure and standard temperature. So the other one's an atmosphere, so I'm going to use 1 ATM. And I always do Kelvin for your gas laws, so 273. So P1 is 1.0 ATM. P1 is 273 K. And they said the pressure's changing to 2, so there's a P2. Temperature changes to 30, there's a T2. But I can't leave it in degrees Celsius. I need to convert that 30 degrees Celsius. I'm going to add 273. So I'm going to get T2 is actually 303K. So I have everything I need. So I'm going to go ahead and solve it. So I'm plugging in combined gas law. Let's see. P1, 1.0, V1, 250 milliliters, T1, 273K, equals P2 is 2.0, V2 is X. I don't know what that is because I said what volume. But my T2 changed to 303K. These are both in kelvins. I'm going to solve for X. Remember, you cross multiply. And X is going to equal 138.7. And now it's milliliters because it's a volume. So thanks, guys, for joining me for Regents Prep 7. You can see it kind of had a lot with our heating curves, had some gas laws, and it had our heat equations. Remember that I can always go to my reference table, and I'm going to think combined gas law. which would have been here, but I rearranged it, so it's right here. And then my heat equations, don't forget, you've got MCAT, MHF, MHV. You can grab all those. And don't forget your physical constants of water in Table B. Thanks, guys.